All right, so moving on to the first example. I took this from Beer Johnson, and because it was a rotating imbalance as we had just described, right? So in this problem here, we have a 180 kilogram motor is bolted to, so this is going to be big M, as we're calling it here, 180 kilogram. I hope I have enough room to fit this in. We'll see. The unbalance of the rotor is a 28 gram. All right, so here's M, 28 grams. And it's located at 150 millimeters from the axis, so E is 150 millimeters in our nomenclature here. And the static deflection of the beam due to the weight is going to be 12 millimeters. The amplitude of the vibration due to the unbalance it can be decreased by adding a plate. Right, so we want to add a plate to the base of the motor. If the amplitude of vibration is less than 60 micrometers for the motor speeds above 300 RPM, right? So no, if the amplitude of vibration is to be less than 60 micrometers, right? So here's going to be I guess I'll use the big X version of this thing. So 60 e to the minus 6 meters. And the speed is going to be 300 RPM. We want to find out how much mass do we need to add to the plate in order for that to happen. So, all right, let's switch little colors, get to purple right here. Some things to do ahead of time. Let's find out what the stiffness of the beam is going to be, because we could take the weight of the motor and divide it by the static displacement. All right, so that's 180 kilograms times 9.81. And we're going to divide by 0.012. Get that millimeters into meters. And we end up finding we have 147,150 newtons per meter. All right, so now that we have that, we can find out what the natural frequency of the setup is going to be. It's going to be the square root of K over M. And this is big M in this case. We're going to just neglect any the little 28 kilograms. It's not really going to affect anything anyway, as far as this goes. So the stiffness is 147,150, and the mass of the thing is 180. So we will get 28.59 radians per second. There's no damping or anything along these lines. We're good with that. Let's turn the forcing speed there into radians per second instead of RPM. So we have 2 pi radians per revolution, 60 seconds per minute, and what we're left with is 31.42 radians per second. We like to use R for our frequency ratio, so we're going to go to omega F over omega N, or 31.42 divided by 28.59. It's important to note that it's greater than 1.099, but still fairly close to 1, so we're getting close to resonance. Kind of a dangerous thing. And I'm trying to see this other piece right here. Let's see the. All right, so we can go back to the equation that we had just expressed, and it has been plotted out right here. And we could use this version of it. Notably, there's no damping right here, so we can ignore that part right here, and we could just plug this in, and then we could solve for what that M must be in order for us to get the the thing that we want. I'll point out first, though, that if we were to do this problem, it probably would make sense to find out what the XM currently is, right? So in the equation that I just showed a moment ago, oops, right here, let's go green, looks like this. We have XM. I decided to call it XM right there. Maybe do I want to call it XM? I guess we'll stick with the big guy because that's what we had right here. Right, that's what we're calling that. And then little m, and then E. And all this, I will go ahead and replace in here. I'll call that R, and we'll call that R, right? So this is the version of the equation I'm writing now. We have R squared over square root of 1 minus R squared quantity squared plus we had 2 chi, R and that squared, right? But of course, without this right here, we could reduce to R squared over 1 minus R squared. A little easier to do. So if we were trying to find X, we would say M over big ME, and then R squared over 1 minus R squared. And I would end up with 0. Let's try to remember. I think it's 0.28. Right, those are 28 grams into kilograms. Divide that by 180, and its offset is 150.150, and then 1.099 squared divided by, whoops, almost made a square root. We don't need to do that if we don't have any damping. And I don't need that. Then I guess I could put that 1 minus 1.099 squared, boom. And we end up with a displacement, which is, I guess, 1.358. I think it's an 8. It's either an 8 or 9. I can't read my own writing. I believe it's a 9. E to the minus 4 meters. And just, this is 2.26 times desired. All right, so we had a criteria and we blew it. So now instead, let's go work this thing backwards. This guy. And say we're going to use the same equation right here, or let's say we're actually using the one above, and take M, yep, and flip them around. I think this will work. M times, and then once again, we're going to have, wait, did I mess this thing up before? I think I might have messed this up. Wait a minute. I think this should have been E right up here. Right? So that would have been almost positive. Let's double check back here. Let's see. Did I do the thing right? Yeah, ME should have been up right there. All right. So I just wrote it wrong. So let's see. Once again, we're going to have ME, but this time we're going to use the 60 e to the minus 6. Well, I should just put an X for that. We're in symbol mode, aren't we? And then do R squared over 1 minus R squared. So we can put all those things into place. 0.028 times 0.15 times R squared, 1.099. Ooh, wait. Let me take a second. I think I messed up. I was going through, but our natural frequency is dependent on our mass. Ooh, so that makes it more difficult. I think I recall what I did. My apologies. is I went back and I looked at this other equation up here. Right? This one doesn't have natural frequency in it. All it has is this m. So let's take that guy instead and solve for m. Now I know what I was done. All right, so let's see. Let me say ME omega squared. Okay, so I do have it written down, but I was trying to think at the same time. So here's the x equals ME omega squared. Not omega is the forcing one, divided by the square root of k minus big M times omega f squared, whole thing squared, plus c omega, that's omega f squared. Let's compare that back to what we had. Yes, I think we got it right. And lucky for us, we can get rid of that. So now we can solve for m. So I just went ahead and put the numbers in and did the did the solving. Here enters one of the first difficulties that needs to be explained. I'm going to try to do my best to try to explain it well. I'm not sure I'll be able to, but let me stick this in here and we'll get to it when we get to it. All right, so here's what we want to solve for. M is 0.028, 0.150 for E. We have our rotation at 31.42 squared. We're going to divide by, and you'll notice this is a square root and a square, so all we need is a K. We have the K. We found 147,150. And then minus, here's the thing we don't know, times 31.42 squared. All right, so as we go through the algebra of this, we're going to have to make, we make a first discovery quickly. Because if we just went the way it normally would, we would sig out and we go, I'll write it out slowly, 147,150 minus m times 31.42 squared. Now that's going to equal, well, you can just put a bunch of numbers. Okay, so I'm going to take this 60e to the minus 6. And I'm going to divide out by 3. So it's going to come out to a number. So we got 69,105. Okay, that is what all of this stuff up above divided by 60e to the 6 equals to. Now we can easily solve for m, but when we do, we go m is equal to 79.06 kilograms. And we're like going, well, wait a minute. It starts out at 180, and they ask us how much do we want to add? Adding plate to the base. All right, so what do we do wrong here? Well, part of this is whether we're going to choose to be in phase or out of phase. Anytime, I'm going to find some blank space here. All right, so here we have, notably, we have damping. But you'll recall when we didn't have damping, we had like we went up to there, right up to the resonance, and then down below, we actually went down to here, and so we went negative. So we want to avoid that. We could just say, well, if you're below the resonance, you're going to be in phase. If you're above the resonance, you're out of phase. So we just accept that anything over to the right is out of phase. And there's also going to be two answers for a particular thing. There's this answer and this answer, right? That can happen. So that's actually what took place right here. Is we found out, okay, well, here's the mass that's possible that if you were on the left-hand side. But if you're on the right-hand side, I think I'm saying that right. I might be having them reversed. But in any case, we could try to have this be a negative value. It could go out of phase, if you will, or just flip the phase 180 degrees. So if you do that instead, you're going to have a negative over here, and when this comes over to the right-hand side, you're going to have a larger number, and you'll have this other answer as well, which is 219.1 kilograms. Therefore, this is like we want to say, if you say, but determine the required mass of the plate, right? So we're talking about a plate. We're going to add right in here underneath the base plate right there. So we need to go from 180 kilograms to 219, and therefore is the M of the plate is going to be equal to 39.1 kilograms. And I ran out of space. I should have made the little thing smaller up at the top. There you go. I'll do some more.